Hello and welcome to what I will only call my new project. Hopefully this is the beginning of something. I don't know. I realized that I had to hit the record button at some point, so this is what you get. This is a video for anybody who designs, fabricates, or inspects manufactured parts. Maybe you want to do this work yourself. Maybe you found this video by accident, in which case, no problem. I hope you get something out of it. I've had a lot of time to think about parts and the design of parts. I have a lot of ideas that I think are important and valuable and I want to put out to the world. A lot of this is tied up with geometric dimensioning and tolerancing, called GD&T, which is the language of parts. So one of my little insights, and this is really, I don't know if this is a big deal, is that most of our parts, when we design a part, generally speaking, it attaches to another part, and then other parts attach to our part. And so we have this stack, part on top of part on top of part, and parts grow out from the sides and so on. And then finally at the top, we have a cover. Now, so our part and most of our parts that are on this stack are going to have multiple interfaces to other parts. But the cover plate can sometimes only have one interface because it's at the top of the stack. And so why is that important? Well, for GD&T, a lot of times these interfaces between parts line up as being our datum reference frames that we use on the parts and in the drawings for the parts. And datum reference frame, I think, is actually just one of the trickiest concepts in all of GD&T. I mean, it relies on these abstractions, right? The datums themselves are just imaginary concepts, like just imaginary geometries, planes, axes, things like that. And our parts, of course, our real parts that we receive back from machine shops are not perfect, cannot be perfect, can never be perfect. They always have some deviation, some anomalies, something that keeps them from being perfect. And what we have to be able to do is sort them out. Are they good enough? Should they be thrown in the scrap bin? Should they go to the assembly line to be put onto our products? This is what GD&T, this is what this is all about, okay? So the datum reference frames are just the greatest source of messed up, confusing GD&T that nobody can understand and nobody can do anything with. And so the best way to improve our drawings is to really get this concept straightened out of the datum reference frame and how we apply datums to our features. So one way to do it is to visualize the way that we're going to inspect the part. Visualize if we were going to try to make a fixture that was going to simulate the datums, and it was going to try to simulate the datum reference frames. And so throughout this, when you see my pictures coming up, I made these fixtures in purple. And when you see those purple parts, I want you to imagine a fixture that's been made to an extraordinary quality. The flat surfaces are flat. The surfaces that appear to be square to each other are truly square to each other. These are really highly accurate parts, dimensionally accurate too. Okay, and so for all intents and purposes, they are perfect, or they're perfect enough that we could use them reliably to inspect our parts and to verify whether they conform to the requirements in the drawings. All right, so that's what to do when you see the purple parts. All right, and so saying all this stuff about perfect parts, realizing that most of the time, our parts are not perfect, and we wouldn't really want our parts to be perfect. We don't want a simple part like a cover plate to have to be made, to the nth degree of accuracy on the very best machine tools that are available. No, we want to throw the door open to as many suppliers as possible to produce parts that don't have to have extraordinarily tight tolerances because they don't have extraordinary requirements like that. They're just covering something up. Really, all they have to do is fit into their wherever they go, and the screw holes have to line up, right? Maybe a few other little requirements. Okay, and we'll get into all that. This is where I got to say also the little disclaimer. The GD&T, I notice, not the most popular thing in the world today. A lot of people think, well, why do we even need to do all this? Why do we need to spend all this time on our drawings and these tolerances? Machine tools today are so accurate. They produce parts that are as good as perfect. You know, I'm not buying it. I'm still not seeing that. I see all the time parts that are made not perfect. I see all the time parts that don't fit together and have to go back into rework and have to have somebody fill out a dispo ticket to say that, well, this part didn't pass inspection, but we're going to use it anyway. We gotta do better. We could do better. I think I see a lot of room for improvement, and so for all those reasons, I'm trying to get this discussion going about some drawings that I made for some simple parts to start with, and we'll get more complicated as we go. And if you like what I've done, then that's great. I hope you become a fan. I hope you start a conversation with me. I hope we become friends. If you don't like what I've done, I still hope we can become friends. I hope we can get these discussions going. I hope we can have some debate about this. You know, one thing about GD&T is that there might be several ways to address a problem. There might be some of those ways that are wrong. There might be some of those ways that are more wrong than other ways, or more right than other ways. And so let's try to find the best ways to do things, and let's share that as a community, and let's get that out there to all the new people who are coming up into the industry, and to all the experienced people as well. All right, so let's go right into an example of a cover plate. And that is going to take us to, oh, okay, here we are. So here's a little silly assembly that I made. It's just an enclosure, kind of built around I guess like a welded aluminum frame. Please just try to bear with me and don't get too wrapped around the axle about the specifics of this design. I'm just trying to get these cover plates out there and have a way to talk about them. Okay, so. With that in mind, I want you to look first at this blue cover plate on top. I'm gonna do a little explode here. I put a gasket in there. I don't know, forget about the gasket. Don't worry about the gasket. What this uses is a bunch of number 8 screws that go down through clearance holes in the cover plate. And then those all correspond to, I guess, like a threaded insert, like maybe like a rivet nut. Stuck into this aluminum frame. Okay, so we talked about, as I said, there might be wrong ways to do this drawing, and on that note, let's go into this. Is this wrong? It's wrong. Could you still use it to get a part made? You could. Let's look into this thing. Okay, this is like, I've known a lot of smart people who have asked me to make a drawing, and they said, please, just do it. I know that this is like what they want when they ask me to make a drawing, which is basically to not make a drawing. It's just to say, like, I want to give the vaguest instructions possible, just totally leave it open to the supplier to just figure out how to make this part and get it back to me. I trust them to make me a good part. Well, so this one just says that, it's a loose tolerance part, whatever that means. And I made all this up. Okay, I made the whole presentation up. The whole video is all my stuff. Okay, but this is not too dissimilar from what I think a lot of people want to do. This just says use the CAD model, all features plus or minus 20 thousandths of an inch. I saw that on the website. That's a loose tolerance for a machine part these days. So let's do plus or minus 20. And then let's go out to the views of the part, the dimension views. This one says that we're 100,000 stock aluminum. Okay, this says they got some reference dimensions. These aren't even toleranced or anything. The tolerance, I guess, is that plus or minus 20. It says this is a 12-inch by 18-inch part. Asking for some chamfers so I don't cut myself, and I just want some screw clearance holes for number 8 screws. Well, it's possible that this part could be made. There are machine shops that might bite on this in the world, for sure. And then there are a lot of cases also where this will get thrown back because nobody wants to take the risk on it, or maybe only one supplier really wants to take a chance on this one because the tolerances are so vague. It's that plus or minus 20. It's hard to know what does that apply to. Does that, if I don't like that for, maybe I think like plus or minus 20 is not even necessarily a loose tolerance for 18 inches, the way that I want to fabricate this part. So maybe I say, hey, I got an idea. I'll say it's plus or minus 20 from this edge to this hole, and then it's plus or minus 20 from that hole to that hole, plus or minus 20 from that hole to that hole. And then by the time I get to the other end of the part, I got plenty of tolerance. It's going to be a breeze to make this part. You know, is that wrong? It's not clear. This is not a well-defined drawing, and you know, in the name of simplicity, it actually is going to cause a lot of people to scratch their heads and to wonder, you know, what is the real meaning of these tolerances, especially since I think designers will know that in a part like this, there are secret tolerances, there are secret requirements that are built into this. One thing is that whoever asked you to make this part probably doesn't want the part to hang off the edge of that frame. They probably want it to not get snagged on something, or to have their fingers or tools get caught on it, or have it like stick outside of the volume of the assembly, if you get me. And so that's one. Another kind of secret requirement in here is that these holes all have to line up. The screws all have to be able to go through these holes and engage in those threaded holes in the frame. If it doesn't do that, if you get to the last hole, the last screw, and it won't go in, and you have to take the whole thing off again, and you have to drill out the hole, you know, or drill out one of the holes, and if the part's been anodized, and what do you do now? I mean, that's a setback. You can't have that. You got to have, especially, you know, if it's considered to be an easy part, you got to have the holes line up every time. And so it's a case for calculating our tolerances and figuring out how to size these features so that we can meet these secret requirements that are really there. And so the next few drawings are going to try to address those issues and show some different approaches for how we might go about this. All right, we are back. Okay, so now let's check out this drawing. It's a different approach, okay? This is a legit GD&T approach, okay? So you can see that we got some callouts for some datum features. We got some basic dimensions that used to locate the holes. Let's talk about a couple of the things, all right? So first of all, let's go into the notes. Nothing too special here. Have a look at this flag note here, flag note 5, where I asked for an identification of the part, a stamp, right? That's going to come up in a second. All right, so I call out a datum A feature, one of the big flat sides. I guess in my mind, it's the side that goes down onto the frame. You know, so I call it the thickness at circle I. I didn't do, there might be some GD&T pros out there who think I should take a couple more steps here to define this material and the thickness and everything. You're probably right, okay? But just to speed through, this is the way I'm gonna do it, okay? To keep it a little bit simple for these examples. So I'm calling one side a datum A feature. And then, so here's what I mean by this being, okay, this is like a really traditional kind of datum reference frame. This is the way a lot of people are taught. I think that the standard really relies on this quite a bit in the illustrations. So you have a rectangular part like this. Well, the long edge, one of the long edges, should be a secondary datum, and we'll call it datum B. And one of the short edges should be a tertiary datum, and we'll call that datum C. I put some form control on the datum B feature. I gave it some straightness. You know, could this be flatness? Yes. Could it be perpendicularity to datum A? Yes. I don't know. For a 100 thousandths thick part, that seems a little cruel. I don't know, to the inspector. I just wanted to give it straightness. I think this is good enough. You let me know what you think, okay? So I'm calling that out to a straightness. And then I come down here and I go to one of these short edges, and I call this out with some perpendicularity control, 10 thousandths, to the datum reference frame A primary, B secondary. And now this edge becomes our datum C feature. Now, it's only when I come in here and I make a hole call out that has the datums called out as A primary, B secondary, C tertiary. It's only at this moment that we really create a datum reference frame, with, you know, called this, right, ABC. And that's not really the only special thing about this call out. This call out is really the meat and potatoes of the drawing in a lot of ways. Because this is where we try to make the holes, make sure that they fit. Make sure that the screws fit through the holes, right? All right. So I went way up. This is, I said, a number 8 screw. I went way up in hole size to 219. And I gave it a tolerance like for a drill hole, +6, -1. All right. And then, and you know, why so big for a number 8 screw, which has got a major diameter of 164, okay? That's a really, it's, you know, like a normal screw hole clearance would be like 188 maybe on the large side. Well, it's because I wanted to get to this 18 thousandths position tolerance. To me, that seems about right for a part this length. I wouldn't want to give it much tighter, but I got it. And so I got to crank up the size of that, of the nominal size of the hole in order to get there. So here's some calculations. I don't know if anybody else does these. I hope you do them. You should do them. This is the thing to do. So this is the way I was taught. Let's see what you guys do. So we take the 219 nominal size, and then we take that minus 0.01, or sorry, 0.001 one thousandths, and we get down to a 218 maximum material condition on the hole size of the holes. We subtract from that the major diameter of the screw, 164, and we end up with this budget of 54 thousandths of an inch. And then because this is something called a fixed floating bolted joint, that's because this part has clearance holes and the frame part has threaded holes, effectively threaded holes because the PEB nuts. We're supposed to divide this budget up so that the clearance holes get 1/3 of the budget and the threaded holes get 2/3 of the budget, presumably because it's more difficult to maintain the positional requirements of threaded holes than clearance holes. And also there's no bonus tolerance with threaded holes, and there's bonus tolerance with clearance holes. Hopefully you learned that some other place. I'm not going to talk too much about bonus tolerance, but it's a great thing to think about here too as well. All right. So when I do that math, you know, when I take 1/3 of 54 thousandths, I end up with 18 thousandths position tolerance. You can work backwards from that and say, well, you know, I got screws that are 164 major diameter, and I want, you know, 18 thousandths position tolerance. You know, maybe I want 20 thousandths, maybe I want 16 thousandths, whatever you're thinking. I chose 18 thousandths, you'll see, because it gets me to that 218, and there's a drill size that's about 219.21875 or whatever, 219, okay? And it could be, you know, it could reliably produce holes at least 218, I think. So that's why I went with this. So that's another reason why I went with this combination of numbers. And so that's it. So if you know, the very first thing you can do to make it more likely that this part is going to fit is just to make those holes larger. And, you know, like I did on the assembly, use some washers to cover up those big holes. No big deal. The washers are much bigger. They're like 360 or something. So think about that, okay? And then one last little bit of arithmetic to discuss, I guess, is how we get to virtual condition. This is a really important term. It's a really important thing to consider for all of this, right? So what we do is we take our MMC for the hole size, 218, subtract the tolerance now, 18 thousandths, and we end up with virtual condition 200 thousandths. All right, so what would this look like? So we talked about visualizing the inspection, right? So let's visualize this inspection. And this is just, again, the inspection for these hole positions. Probably most of you know this, okay? This is a little bit of GD&T ABCs, ABCs 1, 2, 3s. maybe literally, okay? Because we're going to be talking about degrees of freedom, constraining degrees of freedom, and this is just like one of the simplest ways to visualize that and why it's so popular. So what we have here is this inspection fixture, purple, okay? So this is, you gotta assume this to be really high quality. And you can see it has, well, it's got this datum A simulator, a large flat surface. a datum B simulator along that back edge, and then it has a datum C simulator that would pick up on one of the short edges. Okay, and then when we go to drop this down, the part has to go down onto the datum A simulator, slide up against the datum B simulator, and then slide over to the datum C simulator. When you put it down onto the datum A simulator, it's going to make a lot of contact. If this is a thicker, stiffer part, it would only make 3 points of contact, right? And it would constrain 3 degrees of freedom. And then when you slide the part up against the datum B simulator, it would make 2 points of contact. This part will make 2 points of contact, and it will it will constrain 2 degrees of freedom. And then you slide it over to the datum C simulator, make 1 point of contact, and constrain the final 6th degree of freedom. And then, as you see in the animation here, all these little pins have to be able to go down into the holes. I guess it's like one at a time. And then let's just like stop this really quick. Stop this. What are these pins? Well, I made these pins at the virtual condition, 200 thousandths. And then they're meant to go into corresponding holes, little slip fit holes, that are at just the right basic position from the datum. They're very perpendicular to the datum A simulator, and they're in very exacting position to the datum B and datum C simulators. And so we have this datum reference frame that we've simulated with the fixture. Okay, and so it's important to know that when you dimension this way, and you dimension a hole as being a certain distance off the edge of the part, off of that datum feature, you're not really saying measure each of these holes like you're not saying measure each of these holes like from the middle of the hole like to the local edge, like right there where it's at, like with some calipers or something. No. You're measuring the position of those holes with regard to the datum simulator. Okay? So, this is legit GD&T. This is textbook. This is right. We're doing everything that the standard tells us to do with the basic dimensions. We're not doing plus or minus dimensions for the hole positions and so on. But what are some downsides? I wouldn't do this. Probably not. I wouldn't recommend that anybody do it. And here's my biggest beefs with it. Okay, it really has to do with the choice of these edges. So these edges don't really have a whole lot of significance when it comes to the location of this part. Why these edges? What's so special about these edges? I mean, I had to go and put a note here that says to put a stamp on this part with the part number on it, so that I can even tell like which side of this part is datum A, and then I can deduce from that like which long edge is datum B and which short edge is datum C features. Otherwise, I don't even really know. And when I go into the assembly and I go to drop it down on top of the frame, I'm not using like one edge over another. There's no assembly instruction probably that's going to say to do that. So why these edges in particular? And it seems like it could cause problems. It could make it so that this pattern of holes, minor problems maybe, the part will still fit probably, but maybe the pattern of holes is shifted too much to one side or another because the part's not being manufactured on center. This sort of asks a machinist as well to like rough out the outer perimeter of the part and then remove the part from the milling machine, put it back down on some other fixture where they simulate datum B and simulate datum C, and then they go and drill these holes in, right? A machinist probably doesn't want to do that. They probably just want to machine this whole part all in one setup, all the outside and the holes, and that's going to make a better part for us. And we wouldn't want them to do that and then have the part fail inspection just because of some silly thing having to do with like the shifting of the holes in the pattern. Okay, and with regard to the edges of the part. So there's other things we might do with that. I'm just thinking about now, but let's just keep moving on. I got another beef with this, okay, which is that we're calling out the length and the width of the part. Oh, let me show you one thing I did, and this is kind of like a good designer tip. Hope you guys do this. I hope everybody does this. So when you put a cover on something that's 18 by 12, maybe you want to bring the edges of that in a little bit, so their nominal size is inboard of that of the edge of the assembly below it. This way, it never hangs off the edge and gets snagged on anything, and nobody hurts their hand or anything when they go to pick this up, or when they brush up against this thing funny, or they hit some piece of equipment on it. Yeah, just have these always with the cover plates. I think bring them inboard, make them a little bit friendlier to everybody involved. Okay, so that's why I got these undersized, and I want to have pretty good loose tolerances. And I came over here. I think this is the right way to do it by the standard. I put a dimension origin, so on both this and this, because these plus or minus dimensions don't really say anything about the datum reference frame, and so they don't really say that like the origin is for this dimension isn't like over on this edge, until I come in and put an origin symbol in there. And I'll tell you what, I'm using SolidWorks. I love SolidWorks. SolidWorks does not make this easy to do. If you can, I should have a contest. See if anybody can figure out how I did this. Okay, dimension origins. Okay, so here's another little beef I got with this, is that these two dimensions, 11.88 plus or minus 20, 17.88 plus or minus 40, these are not really simultaneous. These are taken independently of each other. These are not dimensions that exist within the datum reference frame ABC. What would you have to do if you wanted to inspect these? Well, if you wanted to inspect, let's say the 11.88 dimension, you'd want to have a fixture that's kind of, I don't even know if you need to have a fixture. Like, honestly, like maybe what you have to do is just set this part down like on an inspection surface on the table, on an inspection table. I don't know, that it wouldn't stand up on its own. You have to support it some way, but maybe it's standing up. Maybe it's standing up on a no, not a datum simulator, but like on a surface, an inspection surface. And then we come down here with the height gauge, and we pick up this this inspection surface, and then we come up here and then we touch on this surface, and we see, are we within that tolerance zone, 11.88 plus or minus 20 thousandths. All right, and then when we go to do the other the 17.88 dimension, it's really just kind of the same thing but different. So we're going to stand it up this way and inspect for that 17.88 plus or minus 40. But when we go and put it into our datum reference frame ABC, let's say there's a little bit of a wedge in that that datum C feature. Let's say it's kind of pushing it as far as the 10 thousandths perpendicularity, and it's kind of got a little 10 thousandths gap in here. And then it's also pushing it on the overall length of the part. It's up near 17.92. Well, in datum reference frame ABC, could that little corner out there be sticking out farther than 17.92 from the datum C simulator? Yes, it could be 17.93. Still, you can have a good part. So that's just kind of one thing. And so I think I see an assembly like this where this part is kind of just symmetrically located on there. It's probably just located on center by eye, and really an important, like maybe something important about it is that it be kind of better squared up, and that these edges that they all lie within an envelope, that they all be kind of simultaneous within this envelope. That's more important to me, and I can't quite get there with the approach that I just showed you in that last drawing. And so that's why I would go and try something a little bit different. So we'll do that after the break.